My name is Brian Engelkemier. I'm a flight software architect in the restricted space sector in Northrop Grumman Mission Systems here in Baltimore. We build payloads that go on satellites for our customers. And I want to talk about the challenges of on-orbit integration and test and offer some of our solutions, and I hope to just get a dialogue going, because this is something we've just started seeing, and we're starting to try to figure out how to deal with this. So this is how we want to deliver capabilities. We want to be Tesla. You turn on your car and the next morning you have autopilot. They delivered a new version for you. Or you have a faster car. We all want to be able to deliver software like that. How do they do that? They have test beds that exactly match their hardware. They know what they built. They know what they're running on. They know everything they know about it. They can do that. They have a beta tester network. They can vary conditions that the drivers are in, and they can roll back those beta versions if they don't work. But even with this kind of environment where you know your hardware, people still have problems. Apple had to pull an update a few years ago because of problems. They have the same kind of setup that Tesla has. They know. They built exactly all the iPads, all the iPhones. They built them. They know what they're running on. They still had problems. And this one was really bad. Lexus bricked their infotainment system overnight. Same kind of thing. They know what they're building it on. We're different from Tesla. We don't have any test beds that match the delivered product. We get incomplete hardware. We have simulators that have a software emulation of most of the boards. We have an anomaly resolution unit that doesn't fully match the payload. Our production test facilities aren't available. We get moved out and a new program gets moved in. We can't test like we fly. We can't take it and fly it again. It's already gone out the door and the customer has it. We don't have beta testers. Our customers frown on that. They're our beta tester, and they're not used to that. But like Tesla, we can roll back as needed. We store multiple versions on board, and we can move back and forth between the versions as are required. And we've proven that on other flight systems. And the only flight software version that's verified on the full system is delivered with it. After that, we can't verify the entire set of flight software anymore. Okay, those previous two slides were probably a different kind of beginning than what you were expecting. That was the beginning of my conversation with our customer about on-orbit INT. We had to talk to them about what was going to be occurring, what they were going to see as we started delivering new capabilities. Their main concern when talking to them was the health of the payload and the impact to operations. They have a job to do, and we have to squeeze in our integration and test within that realm. So we had to make sure that no builds have do damage to the hardware. That's pretty easy. We generally don't have anything that's going to do that. Like I said, we support multiple versions on board. It takes less than 6 commands. We underwent an extensive verification process to show that switching versions is easy, and that if there are problems we use a flash drive, if there are problems in the flash drive, that we can recover it. We used what we call VSIL, which is our Symix model for that. We can go in and poke down in the bottom layer in the metadata we can poke and put in recoverable and unrecoverable errors in the flash. And then verify not just flight software that it detects it and know the signature of it when it sees it, but we can also verify our ROPS so that we know that our ROPS work to recover these payloads. So we'll talk about why we think on-orbit integration and test is needed. We're seeing an increased demand from our customers for new features. These are entirely new capabilities. These aren't minor tweaks to existing ones. They're coming going, well, if you did this and this and this, could you do that for us too? And they're delivered either after the payload's delivered to the satellite integrator or after it's launched. Like we've said, can't be performed in traditional labs. We can't do integration and test there because we don't have everything we need. And it's going to require some changing in developers' thinking and in the customer thinking. They have to realize now what's going on and that we are doing integration and test on an operational system. So I think on-orbit integration and test is here to stay for several reasons. One, we're seeing increased CPU capabilities. We're now flying laptops. Okay, they may be 5 or 10 years old, but they are laptops. They have faster CPUs, more RAM. We have flash drives on them. We treat them like laptops, basically, is what we're doing with them. We have a flight software architecture change. We went from a state machine architecture to component-based architectures. Our OFP is dynamically linked, no longer statically linked into one. We at load time, we dynamically link, so we can drop in new components as needed, or updated components. We no longer patch, go in and put jumps in to jump to a new spot in the code and then jump back to the right spot. And we have a higher level of commanding. We're moving some of the processing that was normally done in the ground up onto onboard so that we have a higher level, because we have the capabilities then of doing it. We can react more quickly to things. A switch from ASIC to FPGAs for space systems. We can change FPGAs post-delivery, so there's another reason another part of the integration and test that we have to do, because to flight software, the FPGA is the hardware. That's the interface to the hardware. That's what we're talking to. So if there is a change in the FPGA, there may very well be a change to flight software that we have to deal with as well. And they're seeing the same increased capabilities as we're seeing on the single board computers. And space qualified systems on a chip will only increase the demand for more and more capabilities on board. So we first became aware of this, or our first attempt with a system that was on orbit, and we had to incorporate a major capability change. We were adding new capabilities, and involved both flight software and FPGA changes. It was one of the changes had a change to the power control timeline, just when each piece is powered up and initialized and all of that. We delivered it, went through all of our verification, had no problems, delivered it, customer installs it, works the first time, works the second time. We're about ready to have the release party, and the customer comes the next day and says, it didn't work last night. Now what? So we said, well, what didn't work? Well, we'll get you the information. So several days later, they get us the information. We look at it, we don't know what's going on. Can you try it again? Yeah, we'll try it again for you. They try it again. It worked. Oh, good. This is really the kind of problem we want to deal with like this. So we couldn't reliably replicate it. We didn't meet the timeline 3 out of the 10 times they tried it. When it worked really well. We couldn't reliably replicate that on our ARU. When we were trying to do it, 9 out of 10 times, the 10th time is when it failed. We tried it. Oh, it worked. It worked. It worked. So you sit and scratch your head a little bit and go work at it again. Took us 3 months to find the root cause and 1 day to fix it. The new capability, why does it take that long to discover the root cause? Well, one is we have to test it with non-interfering basis on regular operations. So we may not, like in a lab, I can sit there and run it again and run it again and run it again. I can't do that operationally. It involves a lot of parties, a lot of communication. So we get an average of less than 1 run per day. We may be able to, that may even be less than 1 per week, depending on what's going on. Like I said, it never failed when we were on verification before we moved it on orbit. Finally, somebody smart thought about, this is an ARU. This doesn't have everything that we have on orbit. And what was making it an ARU was the boards that we were missing were part of the power control that we had to control. So somebody said, wow, maybe that's part of it. So we used WinView to go look, and suddenly the tasks that are in complete contention when you have enough of them are just close enough that sometimes they get into contention and sometimes they didn't. So once we made the configuration change to the timeline, 1 day later it works, and it delivered and the customer's happy. This woke our eyes up to what on-orbit integration and test is like. Opened our eyes, not woke our eyes. So sometimes timing's fortuitous. Everything lines up. There's a different program at about this time when we were going through this that came to us with a big pile of money and said, okay, not that big, and said, here, we want you to add these things. And we said, well, we can't add them right now. We can deliver them after launch. And they said, okay, that's fine. We want these things. So because we knew about the other program, we said, we better start building in stuff to figure out to work on how we're going to integrate and test on orbit. So we looked across all the programs that we had going on at the time at the existing integration test and verification tool sets. What are we using now? How can we get something like that on orbit? And we had to think not just what the tool is, but what answers does it provide? What information out of it do I use? Not just what's the tool. We came up with a series of recommendations. Some of them are tied to the specific capabilities being developed, and some of them were universal. And that's some of what I'm going to talk about here. The flight hardware was being built, which means we couldn't change the hardware. So we had to limit what we could get in. So that limited our scope on what we can get into the system. And ultimately, it comes down to the customer and sees how the sausage is made. They never see the times that you try to load it and suddenly the dynamic load doesn't work. There's a missed symbol somewhere. Now, so we had to explain to them, help them understand why it was going to take longer, help them understand what was going on, why it's going to take longer than what it would take if we were all doing everything on the ground, and why existing capabilities may break. We have a C++ in our component-based architecture. We use C++. Sometimes you do have to change that base class, which means everybody then changes. We had to explain to them, no, we don't want to copy and paste the code over and over and over. So some of what's going forward, all of what's going forward is talking about this new program with Mr. Moneybags here. We're going to be talking about that. Some of this is some of the education we had to give to the customer, and some of it was our analysis of what we do. So pre-launch factory, we've got a development process. It's tuned, it's mature. We know what we're doing. We have a lot of resources available. We have the Symix model that we're working with. We have a partially populated test benches, and ultimately we have a full flight system. So we can work in all of these things. The experts and the assets are co-located. We can instrument the hardware. We can put in bus analyzers. We can use scopes. We can use logic analyzers. We can use signal generators. We can use whatever we need. We can have specialized test equipment available for things that are missing. And it ultimately comes down to that we can turn around things in hours or days. Sometimes the hard ones take a month or two, but we eventually get them. And it's all based on this: changes made and tested in minutes. Build, load, run, look at the results, do it again. Now, once you get on orbit, that whole process has to happen, and then this process has to happen. I've got to build now. I think this is it. Now I've got to get it I've got to go through a formal verification to give it to the customer, and then the customer has to schedule time in and get it in. They have to first get it on orbit and then get it up there. So this greatly increases the time. We have to coordinate with the ops, so we're constrained on when we can do this. It's going to run when it runs. We don't necessarily know. We just suddenly get an answer, and maybe we get data. Sometimes we get an answer, and then we get data later. This can turn it into months for easy problems, very easily. And explaining this, this is what we were explaining to the customer and what we're trying to avoid. So we looked at the resources that we have available. We have an anomaly resolution unit. Before we ship, it's called mini payload. It's mini for a reason. It doesn't have everything. We have a space vehicle test bed, or a flat sat, which is mainly just software simulators. Some of them have hardware in the loop, some of them don't, but that gives us some level of confidence of testing. We have the flight system eventually, and that's really expensive, so that's why we don't have two of them. It arrives late in the integration and test effort. It's delivered to the customer, and then that's gone. And that's the last version of flight software to see the full system, to be verified on it. And then the integrated satellite. We can do some testing there, but that's even a bigger asset, and there's even harder contention to get time on that. So looking at what we can do across these, you can see that we can't verify everything until we get to a full integrated system. Even with the flight system, there's still some things we cannot fully verify. We can use other things to burn down risk, but we can't get rid of them. And once we launch, that's all we have left is the space vehicle test bed and the anomaly resolution unit. So, our investigation into flight software tools. This is what our pre-launch test environment looks like. Looked at what do the development teams use, and one of the things we found is everybody looks at the event log file. We can watch that in real time. Our event log file for us is more than just events. It's basically a debug log. We can tune up and down the level of debug that comes out of it. And we can watch that in real time. And you can, if you're good at it, when you're watching it for a while, you start to pick out, oh, that looks wrong. That doesn't look quite right. That's wrong. You know, you can see the woman in the red dress. Sometimes you can't. We have the data from the STI that's monitored in real time, and that gets stored for analysis as well. So we can go back and look at it again and do data mining across runs for problems. We've got a bus analyzer we can plug into the system to check the real-time interaction, see what's going on there. We've got debugging tools, performance and timing monitoring tools like WindView that we showed, that we used for the original effort. We've also got access to the operator's console. There's things you can do there. And until we get that USB port plugged in and somebody up there to do it, we're not going to have that. So post-launch, we've got the same capabilities. The only change is we're either now running our Symix model, which we had before, but we weren't using it. We were using it for more continuous testing, or the ARU. But we still have access to everything. But once we're on orbit, all of those go away. We don't have access to that. We have to rely on the customer to get us the acquisition data so we can go look at it. We have to rely on the customer to give us the information. So what we want to try to do is try to figure out which of those tools we can get access to somehow on orbit. The constraints to our solution. Remember, we're coming in here with this, and we're going to deliver here. So, and hardware is being built at that point. So that's one of the things is we had to work on the existing hardware. We can't add a space-qualified bus analyzer into it. We had to build them quickly because they're not going to delay our launch while we build integration and test tools into the software. We wanted to add them to the launch critical baseline. We did not want to upload them as a separate load because we wanted to fully verify it on the flight payload just in case we broke something. As a side note, this stuff is internally called Mission to Mars because we're launching it with, uploading new stuff just like the rover did. Right? If you launch with enough capability to get up the right stuff, then you're good. So what can we look at? What can we realistically do? So we thought we could realistically do everything except for monitor data from the STI in real time. Everything else, event log file in real time, well, we'll get close, not really, but we'll get better than we've had before. So timing information, performance monitoring. Early in our programs, we build in the capability to monitor, to gather timing information. It's like a stopwatch. There's begin-end blocks that we use all over the code to track activities. And it tracks it per task and per activity. So this event name is an activity, and then you can see the task names over there. We turn it on and off via config files. This shows wall time. We can also track CPU time. So, you know, if you only used 5% of the CPU during that wall clock time, you'd see the 5% that you were using. It's reported in the microsecond level, and we get a CSV file out of it. We usually leave that code in just in case. And one of the reasons is that flight software uses this to check interrupt response timing. We create events. Our requirement is that we have to hit with 20% margin our interrupts. Update the hardware with 20% margin. If we miss that but still hit the whole time, if we're still under the 100%, we flag it as an event so that we can see it in the ELF so we know something's going on. Something's not right. We're not seeing stuff. So that's part of the reason that it's kept in. Another thing we have, so this is turned on via config files. Our configuration files we have commands to allow us to change configuration parameters on the fly. So that's what we started doing, was being able to build in this capability. And we added that to the list of commands that can be used operationally to change that. And then the CSV file is written on a RAM drive, and part of our maintenance file dump commands allows us to pull any file we want off the RAM drive. So we would just bring that down then. Another one is WindView. So WinView tracks everything in the system. You can see task switching, you can see the network tasks, you can see all the tasks, you can see all the semaphores, you can see everything that's going on, system events. We added the capability to run this by command. So we can have WinView run, it creates its file, we send the file to the RAM drive and then bring it down to the ground again where we can look at it. We verified this capability on the full system as we were going into environmentals. We unplugged everything and said, here's our chance, let's go run it. So we went and ran it, and could see what was going on. Next up was a bus analyzer replacement. So before we started using the CIMIX models or VSIL, early development, flight software was development on multiple SBCs in a rack. And there's no hardware there, just the SBCs. So we can check out the plumbing, we can make sure that the software is talking, all that stuff, the software bus is running, all that kind of stuff's working. It's running with the PCI library. The PCI library properly detects that the boards aren't there, and we added the capability to say, if the board's not there, direct the writes to a log file so that we could look at them and see, are we writing everything like we're supposed to? Like the hardware developers or the systems guys tell us we have to write. So we directed it to a log file. So we could do that testing on those boards without tying up, when the hardware showed up, without tying it up. The code was left in after we got VSIL models working. We no longer use those racks for the system, for the ones that have a VSIL, for the programs that have it. But it's part of the Northrop Grumman standard library, so we just left it in. Didn't want to take it out. It's a good thing, you know. It's there now. So we just had to change it so that it's doable by command instead of whether or not the hardware is there. So you can turn it on even if the hardware is there. We may miss timeline, but if we're that down in the weeds trying to figure out a problem, it's okay to miss timeline as long as you can get an answer out of it. And then recently, the digital folks developed a tool to read that file and feed it into their simulation so they can simulate exactly what we're running now. Not something we anticipated out of that. We anticipated, us going down the list going, yeah, that's exactly what we're supposed to. They're now running that through their simulations. So the event log file, or ELF, this is the right time of year to talk about ELFs. We don't have real-time access to that. We can't get real-time access to that. But the normal ConOps dumps the ELF before the payload's powered off so we could see it. It's stored on a RAM drive. We use lots of RAM drives for different storage, for different things. When an SBC reboots because of a problem, we lose that ELF. We lose the entire ELF. We try to save enough information, breadcrumbs around to tell us what's going on, but even if we were to save like the last 10, 15 lines of that ELF, the problem's probably 100 or 200 lines back that triggered it. So we changed it so that we can write it optionally to a flash drive, only on reboot. And that allows operations to dump that at a later point because they know what the file's going to be. And then if we turn this capability on when we're debugging a tough problem, operations can dump it at some point for us and get us that. So we now know what happened before the dump. Normally we see that, if we're in a lab, you'd see that because you just scroll back through the real-time window and see what was going on. Because Flash is limited life, we keep that by default off. We only turn it on when we need it for these kind of problems. Single board computer access. There's lots of tools to run. You can load up a file and run it. It provides you new commands. You can run that. So you can write something real quick that hooks into the bus to figure out something. So we developed the ability to run secure scripts just like they were run in the command line from there. They're stored on RAM or flash drives, so they can be uploaded as part of the command set, or stored in the flash when we know we're going to want to run it more than once. And again, we capture the output and write it and download it operationally. So looking back on this, the lessons learned were that we have to work with people, you have to work with customers, because the first delivery capability, not that it may not work, it won't work. Eventually it's going to fail. It may take the third run to fail, but it's not going to work. Some of our customers force us to remove code that's not needed for mission requirements. If you're doing on-orbit INT, this is a mission requirement, so you have to convince them that these capabilities are needed, that they are a requirement. I know we were talking about that earlier today. Timing measurements, tracing, logging, all of that has to be automated and a way to get it down. Needs to be a priority for all involved parties. User segment, ground segment, space segment. This has an effect on the ground segment in terms of tasking and in terms of processing data. For a specific, they have to be able to swap in different command set tables based on what's going to be running in a collection window. That's a lot of work for them that they had to take on as well, not just for flight software. On-orbit INT's needs are going to continue to grow. We're only trying to fix the problems. If only I had that tool to fix this problem, you're just going to get smarter as you're going along. So we always have to plan for that. And test software and FPGA needs to be considered as well. For test software, we had a few things. One was our Symix model. We updated the timing to make it much more accurate than it was in responses to match the hardware, so that the program that originally kicked this off, that may have made it easier to find this problem. If they had had a VSIL, two had accurate timing on it. Test software is also being changed for right now in a lab. The test software knows the data is going to show up, and it'll kick off and start running the analysis tools. The data is just going to show up whenever it shows up from the customer. So it's now, we have to have it now just ready and waiting for something to show up in its mailbox to go run automatically. Another change that we're working on, have not implemented yet, is a make file for analysis results, if you will. I want to know what version of the analysis tool did I run on that data set, because that could have bugs as well, and it may give me wrong answers. So I have to then, if I find a problem, I have to know what do I have to go back and run that on to say, oh, that was leading us down the wrong path. FPGA needs, we are, basically all we've done for that is they've told us here's a memory of area to dump at some point in the process, dump that area, send it down in the metadata, and then we'll, unfortunately, then that stays there forever because we don't want to change the ICDs that much, so that continues to go on even after you deliver the capabilities. But FPGAs are going to be an even bigger problem as we go to systems on a chip. How do we get that data out? What's going on there? Maybe it comes out as part of the data stream. That's something we considered. And then, so last, this slide's much more effective until corporate communications got a hold of it. Imagine a gentleman here that was very interesting holding a beer bottle. Yeah, corporate communications wouldn't let me stay with that one, so it's much more effective with the whole picture. And that's it. Any questions?
We as software engineers are always pointing fingers to hardware, and hardware is always pointing fingers back to software engineers. And
Yep.
for the most part, when you get diagnostics down from a spacecraft, you're kind of looking at a surrogate indication because it's secondhand. It's sensed at the time, a time period that you can manage, that kind of a thing. Most of these cards come with like a JTAG interface or boundary checking interfaces and things like that. Have you looked into interfacing that and bringing down that kind of information, especially with the FPGA interest? And then the second part of the question is, logic analyzers are like little tiny things now. I mean, they can fit in your pocket and hook up to a USB port.
Right.
And it'd be interesting to apply some real-time logic analysis that we can put on flight also. So I just think this is fascinating stuff.
Yeah, as far as JTAG goes, we're starting to remove it from our boards. They don't use it. They get everything they want through the PCI interface, and they just.
Okay. I mean, the JTAG interface actually can.
Yeah.
Run
I mean,
through
I looked at them and said, "Are you sure?"
Yeah, exactly. Right.
You know, and I'm the last person you want to see with the screwdriver. I mean, that's not. But I like the logic, the small logic analyzer. That's a. Yeah. Have to think about that one.
So this fundamentally presents a different tool chain or a different development path, and the fact that you're, now doing testing in flight, essentially. One is, how have you tried to integrate some of these, the differences in process into your normal flow? Earlier on, has that actually happened, or do you see this on-orbit integration and test only happening in that kind of realm? And the other is how do you end up trying to train your operators? I mean, basically, you're sort of spreading your entire development over the entire life cycle,
Yes.
okay,
Yeah.
of it. So one is that your operators, although you don't want to have them being debuggers, they in essence could be or need to form that function.
Right.
And the other aspect of it is that you don't want to be testing a new tool once in flight. You want to be testing that on the ground over and over. So you want to try to reintegrate those tools,
Right.
and use them as often as you can. So
Which is why we wanted to get them into launch critical baseline. We did use them, a couple of them we have used. Like I said, the ability to log what we're writing to an FPGA, we've been using on the ground for the processes. We did verify the wind view running, excuse me.
In response to your question, which was, the ops or the actual application of this technique will be very different for low Earth orbit, lots of science data, versus a spacecraft that you're literally loading the mission's software to on its way to Mars or wherever it is, where you can do all this diagnostics offline where there's no science. Or with low Earth, you're going to have to squeeze it in. It's going to be a problem.
Right. And yeah, every operational scenario is going to be a little bit different.
Right.
But
And
it's,
Well taken. Actually, it goes even more general. We spend more time in software development in phase E and F many times than we do actually building the spacecraft.
Right, and as far as working with the operations, because of our environment, I don't really interact with them as much. So the beginning of this presentation, the ground segment developers were there. I had representatives from them, and getting them to buy in on that. That has been a hard problem for them to solve. Is version 1, version 1, version 1, version 2 commands, version 1, version 1, version 1. That's been a hard problem for them to solve. They did not go in anticipating that kind of environment.
All right.
Right.
Thank you very much,
Thank
Brian.
you.
That was a lot of war stories there. Good. Thank you.